Greetings and welcome to another VMBlock screencast. In this screencast, we're going to cover the anatomy of an Ethereum address. We'll run through how an address is created and how to secure your transactions on the Ethereum blockchain. We're going to run through some demos on step-by-step process of creating a private key, generating a public key from the private key, and then generating a public Ethereum address from the public key. So let's take a look at the contents of today's screencast. So, first of all, we're going to dive into the anatomy of an Ethereum address. Basically, we'll just take a quick look at what does the address look like and how we generate it. Then we'll look at digital signatures. This is because we want to know and explain how does an Ethereum address, how is it used in terms of sending transactions from your account to another account. And the answer is digital signatures, which, as we'll see in a bit, uses the associated private key. We're going to quickly look at the difference between externally owned addresses and contract addresses. You may come across this term during your journey as an Ethereum blockchain developer, and it's important just to distinguish the difference between the two. We're going to dive into basic cryptography that's used in Ethereum, in particular the cryptography used for creating Ethereum addresses, which is public key cryptography that uses elliptic curves. We will then actually create a new Ethereum address, and we'll go through all the steps that are required to do this. And we'll use a practical approach, and we'll also use some examples using code, CLI tools, and some online tools to help us along the way. And then, probably the most exciting part and the bit that you want the most, we're going to actually receive some Ethereum or Ether to the new address that we've just generated. The last bits of the screencast will just cover some address formats, as well as EIP55, which is a checksum approach for checking the validity of Ethereum addresses. So, let's have a look at the Ethereum address. So as you can see, a typical Ethereum address looks like this. It is a 42-character hexadecimal string or hexadecimal number. It's always prefixed with the 0x for Ethereum, and then it has this long string of numbers and letters, which is a hexadecimal number, essentially. Now, this is not very memorizable, not user-friendly. It's certainly not like a website address, but we can use wallets and so on to store these addresses if we want to, and then associate a label with them. This is something we'll look at later. So, how do we derive this address? How do we create this address for ourselves? Not this particular address, but a new one. So the first thing we need to do is to create or generate our own private key. And as we'll see in a bit, a private key is essentially just a random number, but a very large random number. So we need to basically be able to securely create a random number, which we will use as our private key. The second step, once we have our private key, is to derive a public key from this private key. And again, we'll look at ways that can be accomplished using CLI tools and code. Under the hood, this uses elliptic curve cryptography. And the final step is to then yield the Ethereum address from the public key. And the way this is done is using a hashing function. And we'll give more details in a bit. So, let's take a look at the properties of an Ethereum address. What makes an Ethereum address useful and valuable for us as blockchain developers and as users of the Ethereum ecosystem? So one thing is to note that addresses are actually anonymous. And you can probably see that from the address I just showed you. And if you look on Etherscan and you have people send you addresses, if you didn't know who that person was who sent you the address, or if you just look at Etherscan, and look at the transactions going through the blockchain, there's no way you can associate that address with someone specific on the internet or in your community. So they're anonymous. The other thing to note, and this is important, that addresses can and probably should be created while offline. So you don't need to be connected to any network. You don't need to be connected to the blockchain. This is something that is done while offline. And we'll look at that in a second. Now, addresses also, it's important to know, can be created for free. So if somebody is saying, hey, I'll generate a new address for you and it's going to cost you $100 or whatever, then it's really not necessary to spend that money. Unless, of course, they're a consultant and you want help with that. But otherwise, it's important to understand that addresses are free to create. And really, the reason is because an address is essentially based on a random number, which is your private key. And so that's free to do. As mentioned before, Ethereum addresses have a length of 42 characters. This is kind of easy to remember because 42 is the meaning of life after all. Ethereum addresses can be easily represented as QR codes. This is a really useful fact because we can now express Ethereum addresses using QR codes in our applications that we develop, and we can also use that knowledge to store Ethereum addresses in our own wallets. So it's a pretty useful piece of information and probably something that I'll cover in a later screencast. Public keys are used to create the Ethereum addresses. This is what I mentioned earlier, and we're going to go through how that can be achieved in a bit, in a demo. And private keys are used to control the Ethereum account. So this is where it's important to understand the difference between public keys and private keys. So in Ethereum, essentially your public key is your Ethereum address. It's not the full public key, but it's derived from the public key. And the address is what you can share to anyone. You can put your address on your website, send it to your friends on Telegram, and so on and so forth. And your clients or your customers or people who want to send you Ethereum can use that address to send Ethereum to you. And you could think of your Ethereum address just like your account number in your bank. You send your account number to somebody if you want them to pay you, just like you would now send your Ethereum address if you want to be paid in Ether. Now, importantly, the private keys are used to control your account. By control, I mean it gives you full access to the account so that you can spend the Ether in that account. So you can do whatever you like with Ethereum that is inside your account if you have the private key. So it's important to keep the private keys private and not share them with anyone. And that way, anytime you receive Ethereum, you can now do whatever you like with that Ethereum, but you never share your private key with anyone. So this leads me on to digital signatures, which is a topic I can dive deeper into later, but I just want to explain the purpose of digital signatures and how they relate to your private key. So a digital signature is essentially a way of signing a transaction payload on the Ethereum blockchain using your private key. So this is a way of cryptographically proving that you own the account that you are requesting a blockchain miner to approve a transaction to move some Ethereum from your account to some other account. So in other words, simply put, if you have a wallet that has the private key of a particular account already saved into that wallet, then you can ask the wallet to prepare and sign a transaction payload and then submit that payload to the blockchain. And essentially what it's doing is it's signing the transaction using your private key as shown in this diagram, which generates something that is not human readable, but is cryptographically provable that you are the owner of the associated private key of the Ethereum address which you want to withdraw Ethereum from. So that's a quick overview of digital signatures, but it's worth diving into that more deeply, which I will do in another screencast. So the Next thing I want to cover is a topic about externally owned addresses versus contract addresses. So an externally owned account is essentially the accounts that we've been discussing up until this point. These are Ethereum addresses or Ethereum accounts. I may use the term address and account interchangeably, but essentially these are the accounts which are owned by individuals, and those individuals have the private keys stored somewhere, typically in a wallet. So these are individual accounts, individual private accounts, versus a contract address, which is a deployed smart contract. So when you are a dApp or a blockchain developer and you need a smart contract to be deployed on the blockchain, you will get a contract address assigned to that smart contract, and that is essentially where your contract lives, but it is not backed by private keys like an externally owned address is. So later on, as we start to explore the blockchain and as you start to grow and experiment with the blockchain, you'll see the difference between the two. But essentially, think of it as a privately owned account that has private keys versus a smart contract that is a series of code and functions that live on the blockchain. Of course, we're going to be diving very deeply into smart contracts as well later in another screencast. Private keys is the final thing I want to cover here before we go into a demo. So a Ethereum address, as I mentioned before, is derived from a private key. Actually, as I mentioned, it's derived, first of all, the private key is generated, which has to be a completely unique random number. And this private key is used to generate the public key, which is used to generate the Ethereum address. So a private key, as I mentioned, is essentially a random positive integer that is 256 bits long, or it's 64 hexadecimal characters. Now, it's essentially like picking a number between 1 and 2 to the power 256, which is a 78-digit number. It's almost like, you can imagine it being like a padlock with 78 different cogs, and each of those cogs has a 0 to F hexadecimal character on it. So it's an incredible amount of combinations that can be used to generate this number. In fact, it's such an astronomically large number that it's essentially equivalent to the number of atoms in the universe. So if you can imagine, that is a very, very large number. This means that private keys are generated in this way are incredibly secure. There is a very, very, very low chance of them being generated more than once, so there's a very low chance of a conflict, and it is impossible to guess. And moreover, as mentioned earlier, and as you will see, when a public key is generated from the private key, this is using elliptic curve cryptography, which is a one-way function or a trapdoor function, meaning that it is impossible to go in the opposite direction. So a public key can be easily generated from a private key, but it is near impossible and requires an infinitely large amount of computing power to go in the opposite direction. So that's why with this form of cryptography that is used by Ethereum, it is incredibly secure. And when you send your public key to anyone, you can rest assured that it is impossible for them to ever derive your private key. In other words, it's impossible for them to gain access to your account and spend your Ethereum that you own. So this is what we need to do first, and this leads me perfectly into demo time. So we're going to now generate a new private key using some of the crypto libraries that come along with Node.js, and we'll also try it out with a web application. So I'll see you in the demo. Hi, and welcome to the demo where we're going to be generating a private key to use for generating an Ethereum address. So this is the first step in generating an Ethereum address, and probably one of the most important parts, because this is the part which you must ensure that it's done securely and that it's done privately. So let's take a look at a few approaches that we can use to generate a private key. So the first approach we're going to take a look at is using Node.js. So let's just first of all check the version of Node that I'm running. So it's version 14.16.0. And the great thing about Node is that we can generate a secure random private key using the crypto library that comes with Node.js, and we don't need to install any other dependencies. So I'm going to bring in the crypto library here by requiring it. And then I'm going to use the crypto library to generate a private key. So I call crypto random bytes, and here I need to pass in a size. Now for a Ethereum private key, the length of the key is 64 hexadecimal characters long, which is 32 bytes. And so we get a bytes array or a buffer of 32 bytes here, and then we can convert that to a string, and we can pass in that we want that string to be hexadecimal. And that's it, right? We can now console log the private key out using console, and we can run the program and see what this generates. So let's go down here and run the program. We just run node and then generate private key, and there is our private key. This should be a 64 character long hexadecimal string. So we can check that here, and it is 64 characters long. So that is a randomly generated private key. Now you might be wondering, well, how is this cryptographically secure? Where did the entropy come from? The entropy, of course, being the seed that assists with the pseudo number random generator to create something that is cryptographically secure and as random as possible, that avoids any chance of guessing. So I'll just give you an example. If we didn't use a good source of entropy, then it could be hackable. For example, if we used a timestamp as a source of entropy, then generating private key from this would be guessable and hackable because of the seed phrase being a simple timestamp. And so you can use that kind of random number generator for things like games, but you wouldn't use that for something that is for your private key, for your Ethereum and for your crypto funds. So how does random bytes introduce entropy? Well, the short answer is, under the hood, it uses OpenSSL. And in particular, it calls the rand bytes function of OpenSSL. And this is operating system specific, and it generates the entropy from various open source parameters that are introduced from the underlying open operating system. So if you want to dig into that, then please check out this documentation to figure out and look at how entropy is introduced into the function. So we can rest assured that the library that we're using with Node.js, the crypto library, and calling random bytes, under the hood uses OpenSSL, which is cryptographically secure. Okay, so now I want to move on to showing you a couple of other examples of how we can generate a private key. These are not using programming tools, but these are using utilities that are available for free on the internet. And the first one I want to show you is a service called Bitaddress. Now I've got it open here already, and as you can see, it is actually an open source JavaScript client-side Bitcoin wallet generator. Now, you might be wondering, well, why am I going to use a Bitcoin wallet generator? Well, this will generate a private key, and as you'll see in a minute, it will generate a private key specifically for Bitcoin, but we will convert it to Ethereum. So I'll show you that in a second, but before I do so, I want to just show you that I am not connected to the internet. So as you can see here, you have to trust me on this, that we're not connected to the internet. And this is just to show you, as mentioned in the previous section, that we can generate private keys without connecting to the internet, even using one of these tools, because I've already downloaded this app and now I can generate my private key. So the way to generate the private key is actually to introduce entropy. And the way that we can introduce entropy in this application is to simply move the mouse around the screen, and as we do so, it creates this trail of green dots, but more importantly, it's generating this key in the middle of the screen here. And when we reach 100%, it will redirect us to show us what they call the share, which is the Bitcoin address. This is the equivalent of the Ethereum address, and the secret, which is the private key for your Bitcoin address. Now, as I mentioned, this is specific for Bitcoin, and this key length is 52 hexadecimal characters. Unfortunately, Bitaddress provides this wallet details utility where we can copy and paste the key that was generated and click View Details. If we do so and then scroll down to the bottom, we can see here a hexadecimal formatted 64 character version of our private key. And this is the key that you can now use to import into your Ethereum wallet to then use as your Ethereum private key. We'll be doing that in the next sections, but for now I wanted to just focus on generating the private key. So that's one utility that we can use to generate an Ethereum private key. Another utility is a service called Vanity-ETH, and if we scroll down to the bottom of this page and just click on generate, again I'm still offline, and so this page was loaded before I did this and before I disconnected from the internet, but I'm generating this while offline, and the private key is here. I can just click to reveal it, and now this private key is what you can use to import into your wallet, and it should yield this address, and we'll take a look at that in the next sections. But for now, I just wanted to let you know that these are the approaches we can use for generating private keys in Ethereum, and that if you want to be secure, especially when using some of these online utilities, be sure to disconnect from the internet, generate the key, copy the key into your wallet and import the key into your wallet, close and lock the wallet, close the website browsers, and then reconnect to the internet. So without further ado, let's move on to the next example, which is generating our public key from our private key. I'll see you there. In this demo, we're going to take an existing private key and generate a public key from that private key. And we're going to use a library called SECP256K1-node. Now, this is a library that actually provides native bindings to the Bitcoin Core implementation of the SECP256K1 library, which is written in C. And it's an elliptic curve digital signature algorithm library, essentially for the purpose of converting private keys into public keys. At least that's what we want to use this library for. Now, the elliptic curve digital signature algorithm is an incredibly secure algorithm for generating these key pairs so that we're able to confidently share our public key, safe in the knowledge that there is no chance of our private key being derived from the public key. This is because the elliptic curve digital signature algorithm is a one-way function or a trapdoor function. This means that you can process it in one way, but you cannot process it easily in the reverse direction. So in our case, we can very easily create a public key from our private key that is going in one direction, but it is infeasible and a very difficult task to go in the opposite direction, if not impossible. So with that in mind, we can use this library to convert or to yield a public key using the elliptic curve algorithm to generate our public key. And so, as you can see here in the example, they're using the same crypto library from Node.js that we used to generate our private key and the random bytes function, and they're importing this library, and then they generate the private key here in this section. Note that they're also repeatedly verifying that the private key is valid. This is just to make sure that it falls in line on the elliptic curve to be able to generate the public key. We didn't do that in the previous section, but this library is doing this in the example here. And once a valid private key is generated, then it's passed into the library's public key create function to output the public key. And this is essentially what we want to do in this example. So over here in our IDE, the first thing I'm going to do is check the version of Node that we're using, which is 14.16.0. Since we need to install dependencies, I'm going to initialize a new project here using npm init. And then I'm going to install the library secp256k1 from npm libraries and from the repositories. So we get that installed like so. Next, I'm going to begin coding out the functions to be able to convert a private key to a public key. So the first thing I want to do is I want to import in the public key create function. So public key create from, whoops, not from, but basically I need to require from the library I just imported there. So that's the function that I'm going to be using. Next thing is I need a private key to use for this example. So I just happen to have one over here which I'm going to use. Of course, note I've never used this and I never will. And then I'm going to create a buffer from this private key like so. So I import the private key here and I output a hexadecimal buffer. And then in order to generate our public key from this buffer, I'm going to just basically create a const, if I can type, of course. So this will be a public key. This will be my public key. And it'll be a new buffer from the public key create function, which I will pass in the private key buffer. And I will then convert that to a string, a hexadecimal string. So I just pass in toString hex like so. And finally, I can console log out the public key like so. So we just say public key like that. And with that, we should be able to run this. So if I do node generate public key from private key, we end up with our public key as shown. Now, one thing to note is that if I just open this in Node and check the length, then you'll see it is 130 characters long. And actually a Ethereum public key is 128 characters long. And so the reason for the extra 2 characters is this prefix here, the 04. So whenever you see a 04 in with an Ethereum public key, that basically means that it is a non-compressed public key. So generally speaking, the public key that you want to use is actually the characters without the 04. So I'll just paste that in there so that we can use that. Obviously, you know, when you're writing applications and you want to generate public keys as part of a process, then you may look for that 04 prefix and remove it accordingly. Okay, so in the next section, what we're going to do is convert this public key into an Ethereum address. So let's see you there. So previously we generated a public key from a private key using Node.js, and we wrote the function ourselves, but there is actually a utility that we can install that provides a command line interface. So I just want to quickly demo that. The utility is ethereum-private-key-to-public-key, and we can install it as a CLI down here by running npm install-g and then the library that we want to install. And once that's installed, it is essentially installed in the global space, meaning that we're able to access it from anywhere, and we can access it essentially as a CLI tool. And so the way to do that is to just run the same command as, not sure what happened there, I just want to copy and paste this here, right? So we want to run the command like so, okay, and we just simply pass in a private key. So let's grab the private key from the previous example, this one here, and it should output the same public key, this one here. So let's go back to the console, paste that in, hit enter, and we get this public key. And you notice it's also prefixed with 04, which, as mentioned, means that this is an uncompressed public key. So if we take this over here and we just compare it with the key that was generated using our code and remove the 04, you should see that they're exactly the same. In fact, we can just highlight it and find in the file that it's the same. So I just wanted to quickly show you that as another way of generating the public key from a private key is to use that utility. Now we want to move on to generating an Ethereum address from a public key. So I've created a new file here, an empty file, and this is where we're going to write the code to do that. Now, quick background on how does Ethereum create addresses, or how do we create Ethereum addresses? And the way is to take the public key that we generated in the previous step, and we simply apply a kekak 256 hash function to that public key, so essentially hash the public key, and then we take the last 20 bytes of that key, and that is essentially our Ethereum address. We will also prepend, I should say, a 0x to the beginning of the address, so that we can then use that and it's formatted correctly. So one thing to note is that we need to install a new dependency which is the kekak 256 hashing function. So we just run npm I and install that. That will add that to our package JSON, and then once that's finished, which it has, we can now require it. So const kekak 256 equals require, and we can require the library here, kekak 256. Let's just copy and paste that here. All right. With that out of the way, what we need is a public key to use for generating our address. So I'll drop in the same public key that we generated previously. And what I'm going to do is I'm going to create a buffer using buffer.from, and I'm going to pass in the public key, and I'm going to specify a hex format for that. And now we're going to go into the core part of this, which is to generate the address using the hashing function. So we can just say Ethereum address equals kekak256, and we just pass in the buffer, so the public key buffer, and at this point we convert it to a string. So we've now got the hash, so we convert it to a hexadecimal string, and the final part is to take the last 20 bytes. So we know at this point that the hash string is 64 characters long, and that we know that 20 bytes in hexadecimal is 40 characters long. So we can use the slice command and say, well, let's take from the point in the string, the index of the string, where that would yield the last 20 bytes. So essentially we're saying the string length is 64 and we want the last 40 characters, which would be the 20 bytes that we need for the address. And finally we can console log that out. So we just say console log Ethereum address, and we can output that by prefixing with a 0x, and we just do a simple string concatenation here, and that should be it. So if we run this, we just do node generate Ethereum address from public key, you can see that it generates this address here, which is the address that we yield from this public key. And a simple way to confirm or check that this address is indeed the correct corresponding address for the private key, we can go over to the file where we were using the private key, and you can see here the address is being shown thanks to a plugin that I'm using in Visual Studio Code that yields the Ethereum address for me, and you can see that it is the same. Actually, the address is being displayed in the plugin using a checksum address, which is a mixture of upper and lowercase characters, something that we'll discuss briefly in a bit. But you can quickly do a check and you can see that the address starts with ECC and it ends in 3CO. And generally that's a quick way that I use to check that an Ethereum address matches another Ethereum address by just checking the first and last 3 characters of the address like that. Now, the next thing I want to show you is another way of generating an Ethereum address from a public key. And again, it is to use a utility, a command line utility, which is the Ethereum public-key-to-address utility. And it's very similar to the other utility that we looked at, which was that generated the public key for us. This is very, very similar. So we basically just install it as a global dependency, and then we can run it by passing in the public key. So let's try that out over here. So we install the Ethereum public key to address library, and then we can run that library by basically running the command Ethereum public key to address, and we pass in the public key. So let's grab the public key from here and paste it into here. Now, the first thing you'll notice is actually it errors out. And this is interesting because this utility actually requires the 04 prefix that we removed. If you remember, we removed that. Then the 04 prefix, it basically denotes that this is a uncompressed public key. So if we reapply that and run it, we get the address. And you will note that it is the same address that was generated earlier. It starts ECC and ends 3CO. I can see that already. If I copy and paste that over here, back to our IDE, you can see that it matches the address generated in our code. So that is how we can go from nothing to an Ethereum address that we know is completely unique, completely secure, and we can start using it to send money to and from. Essentially, at the moment, of course, if we look at this address on the on Etherscan, in fact, here I can just click this and it gives me a convenient link to open the address in Etherscan. So this is mainnet. Obviously, since this is a brand new address, there are no transactions. And on mainnet, I'm not going to use this, of course, because I've shared the private key here in this video. But we can easily send Ethereum to this address by just sending money to this address, but we can do this on testnet because the private key has been exposed. So don't send any ether to this address. But if you create your own addresses in the similar approaches that I just showed you, then you can start receiving Ethereum to those addresses right away, as long as you haven't shared your private key or exposed your private key in any way. If you have, or you think your private key has been compromised, or you think you've been hacked, then remove any Ethereum in that account immediately, or don't use that account at all. So with that out of the way, we can move to the final part of this screencast. See you there. So in the previous sections, we generated private keys, public keys from the private keys, and then Ethereum addresses from the public keys. Now, one very common way of managing your private keys is with a wallet. So I want to show you quickly the wallet that comes pre-packaged with the Brave browser. Of course, there's a number of different wallets you can use, such as MetaMask and Exodus and many others. But what I want to show you here is really how you would take your private key and import that into your wallet, which will generate your Ethereum address that you can then share. So without further ado, let's have a look. So we go over to the Accounts tab and click Account, and then click Import, and then here I select Private Key. And then I'm going to grab the private key from the previous examples, which is this one here. And we should see the same address, the B3CO, ending B3CO address. So let's go back over here, paste the private key in there, and we call this Rien block demo, and we click import. And as you can see, it's created this account. We can click on it, and you can see there we've even got a QR code as well. So that's really for convenience. But as you can see, it is indeed the address that we have seen in the code examples from earlier. So that's a very quick overview of taking your private key and importing that into your wallet. The process is going to be similar for most wallets, and you should see the same address rendered with your private key. Wherever you import your private key, you'll see the same address being produced. Obviously, back in behind the scenes, the wallet is using exactly the same approaches and procedures that we just went through. So another thing I want to show is also wallet based, but this time it's from code. This is the ethereumjs wallet library, which you can actually use to generate a wallet in far fewer lines of code and with far less headache and having to dig into the different hashing algorithms and so on. This basically does everything for you. So this is a convenience library that you can use if you want to create your Ethereum addresses with, as I say, with just a few lines of code. So we can have a look at that. So over here, I've got a new file opened up, which we can actually use. And the first thing that we need to do is install the ethereumjs wallet library into our package. Once that's installed, we can require it in, and then we can call a convenience method to create our Ethereum wallet. On the wallet object, we call the default, in the default namespace, generate function. And that's actually all we need to do, because at this point, if we want to, we can console log out the private key, So if we just take a look at the private key here, that's generated. So this will be eth wallet dot get private key string. So again, it's a convenience method that just outputs that. And let's call another function, which is, let's get the address. Yes, so get address string. And we'll just rename the label here address. And that's it. As you can see, it's really easy. So we can run this using node generate ethereumjs wallet. And voila, there it is, our private key and our address. As simple as that, just essentially 2 lines of code. But of course, if you were to read the source code of the ethereumjs wallet library, you'll see that the generate function under the hood does pretty much all of the things that we covered earlier for generating the private key, generating the public key, and then generating the address. So that's it for this section. So to conclude this screencast on Ethereum addresses, I wanted to just quickly show you this graphical Ethereum address post here that essentially is a graphical outline of everything that we've just covered in this screencast. And it's really nice because it shows you very clearly and nicely what's going on. Something that's slightly different though is that we start off with a passphrase to then generate the private key. So I can just type some letters like, hello, and we get a SHA-256 of this string, which essentially is just our private key here that we can then funnel into generating the public key, which is sort of graphically shown here on the elliptic curve as being these X and Y points that represent the private key. And these are then combined together to generate our full public key, which is then passed through the KCAT256 hash function. And we extract this last bit here, the last 20 bytes, and prefix it with a 0x to end up with our address. So as I type different words in here, and so on, you can see that the address ultimately is generated at the bottom here, changes in real time, and the private key and public key, XY points and the hash and everything all sort of flows through in real time. So and the last thing, so take a look at that. This really a nice diagram to just play around with to get your mind around what's going on with Ethereum address generation using this approach. And speaking of addresses, one thing to bear in mind is that you may have seen or heard of EIP55, and you may have, as a result, seen addresses displayed in a mixture of upper and lowercase characters. And essentially this is for giving the ability to checksum the address so that it makes the address more secure when sending that into wallets and using QR codes and so on. And it's just an approach of basically hashing the address and then uppercasing some of the hexadecimal characters that are in the A, B, C, D, E, F range, and only if the corresponding hash value at that position is greater than, I think, 8, then it will be uppercased, otherwise it will remain lowercase. And that way, because it's been hashed, the address has been hashed and then checksummed against that by applying this rationale, then we're able to validate that addresses are checksum addresses, which just helps you to avoid sending Ethereum to the wrong address and therefore losing your ether. I did mention before that I often will just check the beginning and the end of an address to check whether or not it's the same as some other address, and that's something I do while developing. But if I'm going to send Ethereum to an address that is on the network and on mainnet, then I'm going to be pretty vigilant about checking the address is the exact address that I expect to be sending it to. And so this checksum approach is one way to help me with that. Another way is, of course, to use wallets and to use directories in your wallets. So once you know an address that you're going to be sending Ether to regularly, you can save that address in your wallet and label it with something that is human readable, you know, like Dad's Ethereum address or something, and you can then use that to confidently send Ethereum to that address going forward. So that's it for this screencast on Ethereum addresses. I hope that you enjoyed it, and I hope that you will like and subscribe to this channel, and I will see you in the next one. Goodbye for now.